much. So I've just realized that I'm in the wrong week because I'm mostly working on long range conversion. However, I'll actually mention both short range and long range and how they are separated in the equation of motion approach. So thank you very much for inviting me to speak at this very interesting program. Yeah, as I said, I mostly work on the applications to nuclear structure, a little bit on quantum computation since recently, and I hope to learn more about heavy conditions during this week. So yeah, just want to say I didn't prepare anything about the intersection, just pure nuclear structure applications for today. The work I'll be talking about was done during recent few years in the following collaboration of physicists Peter Schuch, Peter Ring, Mankoba Klachvayo, Ino Zhang, Caroline Raban, and Litvinova. The first two people are my advisors, my teachers, and the others are my advisees, students and postdocs. And before starting, I would like to acknowledge the terrific contribution of Peter Schuch to our work and also to the field of the nuclear many-body problem and the quantum many-body problem more generally. He was mostly focused on condensed matter applications, though. And he unfortunately and unexpectedly left us last year. So I wanted to start with reflecting on this famous picture with the energy scales. So I put them all from atomic to Planck. So what I wanted to pick from here is that for each energy scale, there is a commonly adopted concept. So we basically operate certain effective field theories where
I wanted to hide. There was something covering the top of your slides on that.
so they used to operate certain effective field theories where higher energy degrees of freedom are integrated out explicitly or implicitly. And practically it means that we make some low resolution input into the theory. And in principle, this should work, but in practice, when we input low resolution, we also get results with low resolution. We get very, very general properties of the many-body system quite well. Then typically, these are integral properties, like ground state energies. Sometimes we get the positions of the resonances, collective resonances, well, but not the spectral details. So therefore, we would like to address particularly this issue and rather investigate the connections between the scales via emergent phenomena. So this kind of tension I'm talking about is known as the tension between the so-called reductionism and emergentism. And that's in the very nature of our understanding. So when we operate with Hamiltonian, we have a kinetic part and we have potential part. The kinetic part addresses the center of mass function of the degrees of freedom that we select, and the interaction is something more mysterious. Like when you say interaction, sometimes you say forces or potentials, and everyone means something different. Saying that basically the problem is that this interaction part, it contains the internal degrees of freedom, which inevitably drive us to the next energy scale. So, and this happens at all scales. Basically, I put here the typical the typical diagram that illustrates our understanding of interaction in the standard model. So even on the level of the elementary part, on the level of the most elementary constituents, we have to put an input here, the vertex, and masses, coupling constants, they serve as an input. Although there is a very interesting aspect of the string theory that has no interaction. So basically, you only define the free motion, and it turns out to be possible to describe the interaction without any input. So can this be useful in some respect? I don't know, but we're trying to see how possibly we can derive those interactions in different scales from the underlying. This is presently how we presently understand the nuclear-nucleon interaction. So high energy, intermediate energy, low energy pictures. It should be in principle derivable from each other, but in practice it's not the case. However, by paying the price of effective coupling constants, in principle, even in nuclear structure, we have all three types of interactions in the market. This is the quark-meson model, this hydrodynamics model with the mesons, and there are models with just zero range coupling, both relativistic and non-relativistic. Perhaps you have heard the talks during the previous week about Skirm, density functional effective interactions of the Skirm type and the relativistic, and so on. In the formalism which I'll be presenting, I'll be talking about the generic Bayer interaction, the interaction between two nucleons in the vacuum. So I'll be mostly in this intermediate energy picture. In the implementations. So the generic Bayer interactions, I assume it contains all the channels that describe nuclear-nucleon scattering and bound states. And then in the main body of formalism, the high orders. So I will start with just leading order, and high orders will be treated by medium propagators, which means that I'll be basically addressing medium mass and heavy nuclear systems as well as nuclear. So we try to stay away from the perturbation theory and capture the emerging phenomena, collective effects like this. So in the implementations, as I said, I will use meson exchange interaction with leading order. And this can be also done differently. It can be done with effective coupling constants. And meson masses, for example, we use those adjusted in the mean field level. In this case, we have a technique for correction of given field double counting. And another possibility would be using just Bayer meson exchange interaction, but then we need to do the subtraction of mean field artifacts. This is some work in progress, and I will not be talking about this today. So we start from the general Hamiltonian, and again, for now, we just consider two body forces, although in this formalism, three body forces can be also added. And we work with the fermionic correlation functions or propagators. This is the simplest one. This is one fermion propagator in the medium. So this is two field operators averaged over the ground state of our many-body system. These are single particle variables in time. So when we are here in the Heisenberg picture. The Fourier transform of this object is a spectral expansion shown here. And this basically tells us why is it convenient to work with these functions, because they are directly linked to observables. for example, the poles correspond to single particle energies, and the residues to the spectroscopic factors which can be probed.
Okay, at this point, I would argue that a spectroscopic factor is not an observable, and you could make a field redefinition there and get something different.
Yes, there is, I think this discussion is going for decades. Yes, the spectroscopic factor is observable. I think it is observable, but it depends on the basis.
It's a scheme dependent.
It's basis dependent, because there is this little, so this is very slow thing. I cannot put, I want to put it to this index here, this 1 prime indices. These are the basis indices. So if you analyze your data, you have to do it in the same basis as you do your calculations. That's basically the trick. Thank you very much for pointing.
The question I had is, so you're doing everything relativistically, or are you
Yes.
going to do a non-relativistic reduction?
No relativistic reduction.
What's the motivation to do it?
So yes, there is a very good motivation to do it relativistically. Actually, we know that the relativistic kinematics is not the non-relativistic effects in the kinematics are not very pronounced at low energies. However, we keep in mind that we may have some high energy extensions, some high energy applications. For example, in the experiments that already have been done at different facilities, and they are planned also for the high energy upgrade of FRIP, they measure resonances like gamma-Taylor resonances and charge exchange reactions up to pion mass, and maybe even at high energy. There is a long-term discussion about quenching, so you may have to go to really high energies to prove that. That's about kinematics. However, there is another point here. We have in the relativistic description, it's a higher symmetry description, and we avoid certain hidden correlations between different parameters that you may have in non-relativistic one. For example, if you try to model spin orbit interaction and tensor interaction with SCARM, you vary them independently, while in the relativistic theory, they come from the same, they have the same origin, and you cannot vary them independently, really. So this kind of things, they're not very obvious. Sometimes people argue about the origin of spin, that it's relativistic. It comes from the Dirac equation. However, recently I discovered a very old paper saying that you can also do it with the Schrödinger equation. So I will not bring this up. Yeah, it's coming from the invariance, from the Galilean invariance. There is an old paper from, I can share it. Old paper from a French mathematician who pointed it out, and now it was kind of revived in some research of Oxford people on quantum computation. So yeah, but you can still hear that. You can still hear people saying that spin is a relativistic effect. So okay, this is then our major background. So I will also elaborate on the two-body correlation function. This is another very important quantity. So this is a two-point function here. So, and you will see why we are most focused on the two-point functions. And it has a similar spectral decomposition. And again, we can very conveniently link the poles to the excitation energies. That's basically the spectrum of the nucleus that we observe from a certain probe. And the residues here are composed of the transition densities that govern the transition probabilities and strength functions. So the equation of motion method is a relatively old method. It was introduced by, I don't even know who was first introducing that. I think a lot of work came from Dyson and Schwinger, people back to 40s and 50s last century. However, there are some new variations on that I would like to mention. Basically, what we do, we differentiate our propagator with respect to the time. Say first we differentiate with the time t, with respect to time t. And usually that's the equation of motion you see in the text box. However, what Peter Schuck was suggesting to do, and probably some people before, you differentiate also on t prime and generate the second equation of motion. And in this case, you generate a different form of the self-energy. So in both cases, you generate the self-energy that has a static and dynamical part. And the existence of the static part is basically is stipulated by the fact that you start with an instantaneous interaction. That's what I put from the beginning in the Hamiltonian. So it's instantaneous. That's why, elaborating on the commutators, you get the first term of this form, where the Bayer interaction is contracted with the correlated density. And then this nice symmetric form of the dynamical self-energy, which has the two interaction matrix elements contracted with the three-body Green function or propagator. And this result is exact. So in principle, it should be valid for any fermionic system. Here, I would like to mention that although this part looks very much like Hartree-Fock, it includes the correlated density. And the correlated density is a static limit of the propagator, which is in principle the full solution of the Dyson equation. So it has to have a feedback from the dynamical part. So then we have also this very nice relationship between the propagator of one fermion and the total energy of the system. This is known as Colton-Migdal-Galitsky sum rule. And in this form, it's valid for two-body interaction. So for three-body interaction, it's a bit modified. But essentially, it serves as a prototype of the density function theory. Basically, it tells you that the total energy of a correlated system is fully defined by the Green function of one fermion. So in the density functional theory, this is transformed basically to a static relationship where instead of the dynamical quantity here, that's the Green function, you have the density, that's the static limit of it. However, you have to always keep in mind that although the full energy is determined fully by this part, it gets a feedback from this dynamical part. And a similar structure of the theory is in the two-body sector. So we have the two fermion. In this case, it's particle-Hall propagator, but we also deal with particle-particle propagators. They are all connected, especially in the superfluid environment. So it has a similar equation of motion with the Salpeter-Dyson equation in a similar form of the interaction kernel. And here are the static and dynamical parts of this kernel, respectively. So now we have, again, contractions with the density, but now it's a two-body density. So in order to get the static part, so these are your short-range correlations, basically. So if you want to calculate exactly or accurately the short-range part of the interaction, you need to do, that's basically one type of diagram. You have contraction in all possible ways of the Bayer direction and the density matrix. And again, since this density matrix of two-body character is the limit of this full R. We need also the dynamical part. But dynamical part is again having a higher rank propagators here in between. So in this case, it's G4. Four-body propagator. If you try to generate the equation of motion for G3, G4 that we need for those kernels, what you get G5 and G6, and that's how you couple to the not infinite. But if it's finite system, it has n correlation functions where n is the number of your particles. So if it's nuclear matter, it's infinite.
Just a quick question. This short range correlation here, does this include the short range correlation we're talking about later? I mean, the typical short range correlation between proton neutrons, like the ones that are above the Fermi surface. Does this include that, or this is different short range?
This is a question of terminology. I don't know. You can call them what you want, but this is what comes from the exact theory.
But this is from the mean. The reason I said this is coming from the mean field, right?
There is no mean field here.
Oh, okay.
This is the exact theory.
Oh, I'm talking about the left term. So this bosonic mean field.
So again, so let's go back. So this is the Bethe-Salpeter-Dyson equation for this propagator. So it has this F. This is the interaction kernel. It has static part. It has dynamical part. And this is the static part. And this is dynamical part. This is short range because it has no time dependence. There is a delta here, delta function here. And this is long range because it contains propagators. It has duration, retardation, how you want to call it. So that's why we call it short range correlation. You can call it mean field. It will be mean field if you, for example, well, it's a bit misleading here. Sometimes when you do your implementations, so now I'm talking about exact theory. If you do your implementations, what many people do, they drop it simply. I will explain the connection to the mean field in the next slide. But for now, this is exact. So maybe when I move a bit on, it will be more clear. So we can return to the discussion. So for now, I just wanted to emphasize that we need to know for the accurate solutions, we need to know those correlation functions. And now I want to explain how we deal with that. Because dropping them is not the best idea. So this is a short description of how we deal with the finite or infinite hierarchies of the equation of motions, of the equations of motion. If we want to somehow take into account this dynamical kernels, what we like to do is to somehow reduce this G4 to this kind of cluster decompositions, we can call them. So in this way, the G3 will be then having G1, G1, G1 term, G2, G1 term, and fully correlated three-body term. So this is sometimes called self-consistent green functions, this type of approach. So, and we will be actually in this work, we are trying to retain this G2, the two-body correlation functions coupled to one-body correlation functions. And I will show that they introduce very important effects in the
Is there like a scale that suppresses these high? Like, how can we understand that there's like an expansion and these get smaller and smaller supposedly? Is it like more propagators, more inverse masses, or something like that?
You're asking about cluster decomposition.
Yeah, like would you say you truncate at some point? Like what makes this like a good approximation?
For now, I truncate because I cannot do.
Okay.
For now, I truncate because I cannot strip them. So, but there is some phenomenological approaches which were introduced again back in the 50s, 60s that treated this type of contributions based on some input.
So
Basically, this, I will just show now, this type of structures, they form the emergent effects and collective modes. So, but this is the general, somehow this is the general property, let's say, or feature of the quantum field theory. You know, that's how we cause the decomposition, because at long distances, your degrees of freedom should be separated. But of course, we want to have from theory. So for now, we don't. For now, we just make the step. We step from here to here. Okay, and we keep this two-body correlations in the theory. So that's schematically how we treat G3 then and G4. So only retaining the two-body correlation functions. And then remarkably what happens is that if you put them back in this dynamical kernel that I showed before, they always come in these combinations. So they come in combinations with the interaction matrix elements this way and this way. And we can exactly map this to some emergent effective particles. So we call them phonons. They are known also in solid states. They manifest themselves in nuclei as collective excitations, and they exist both on shell and off shell. So they exist as intermediate particles, and they exist also as collective modes.
Can I ask, when you say emergence, you mean, is there like a technical definition of this? So you're not putting it in the degrees of freedom, you get it out, is that the idea?
Yeah, this refers to the, sorry, this probably refers to some historical aspects of this. In the past, this type of, okay, let me just move to maybe next slide. So that's how the dynamical self-energy of a single particle or of single fermion looks like in this approximation. So we have the radiative correction type contributions. There is always second order term, but usually it's small in big nuclei. In strongly coupled system, you can imagine lowest order is not the leading order. So this is the leading order then. And in the past, these phonons that I have here, they were coming from the phenomenology, from experiment. So their characteristics were inputted based on experimental data. So, but in principle, we see that they are calculable now. So, and you can in principle write.
How you count the order in the first step?
There is no order here.
The second order, maybe.
Okay, second, right. Second order with respect to the Bayer interaction, because there are two matrix elements.
This is not derivative already.
This is not.
So you cannot use a text to count the order.
Yes, I think this is wrong, but this is how people call it in the literature. So it's known as because, you know, also in certain implementations, we have approximations for those propagators here. Can put non-correlated propagators. And then it's second order, and I will explain later. So sometimes you use effective interactions here, and then it's second order with respect to effective interaction. But you're right, this is not really second order. Yeah, in principle, you can rewrite it in the Hamiltonian in terms of this effective particles. So then why not? We think in a similar formalism about the standard model interaction vertices. So probably they are derivable from some underlying structure. A little remark about this type of treatment. There is a problem with approximate treatment of those provocators, and that's related to the so-called Paul mismatch. Positivity or optical delirium. So in various contexts, this problem manifests differently. We have, if you put the analytical forms of this contributions, you see a different nature, the poles of different nature here. However, in principle, it has to be just this type of spectral expansion where the densities of this vertex functions factorize at the pole. And basically, you can even see it here. This comes with the minus sign. And then in certain implementations, it can be a problem. For example, we can get negative cross sections as such. And I just discovered recently there is a similar discussion in particle physics, and positivity there can be handled by what they call amplitude. So I'm not really expert there. I just wanted to mention that probably we can also learn something from this field. And the amplitudes are calculated as areas of certain geometrical structure. Although this is only in certain types of areas, but we may think of a similar. So now, how is this related to the mean field? At least in nuclear structure. So you have, we know the exact self-energy. This is the exact self-energy here. And what the mean field does, it approximates both terms with one term. So it's not that you neglect this dynamical term completely, but you redefine your interaction and you redefine your density. So that's in the nutshell, the density functional theory that we are operating. However, it's not really clear what energy that you have to put in here, or frequency, if you work in the frequency domain, if you want to calculate it from up and down. So typically people don't really do that. They approximate the self-energy by this Hartree-Fock-like term, and then readjust the parameters of the interaction. That's how Skirm, Gogni, and Fayet's functionals are organized. And in the meson exchange, relativistic functionals, the coupling constants and masses are readjusted also accordingly. And then, in principle, the results of these DFTs are relatively good. They are good starting points. We can use them as a basis, and that's what we do when we construct the so-called beyond mean field approach. So we take this as a basis, and then we put this this dynamical part back explicitly. Why do we need this? Because it introduces singularities here and introduces new states, the fragmentation of the states that we need for describing the spectroscopy. This is a two-body correlation function as a reminder here. And then, since we know that part of it is already contained here, we do the subtraction of the double counting of exactly the same thing that we have added, because usually we cannot add all those contributions. We add the most important of them and correct for the double counting. What I wanted to say before seeing here, I wanted to say maybe, let's see, a question in your eyes that this type of radiative correction is divergent in quantum field theory. However, in nuclear physics, it's not. So we have a very good convergence because the phonon spectrum of phonon energy is finite, and it's converging nicely in the implementations with finite range interactions. So I've heard some complaints from people doing Scrum that it's with the zero range it may have a problem, but with finite range we don't have this problem. So now let me go back. I wanted also to put in some comparison to chiral AFT and so-called ab initio methods. I'm trying to somehow understand what's similar, what's different there. So at leading order, we have basically this correspondence. So we have the mesons, which are most important. We can add also other mesons here. In chiral AFT, you have heavy mesons as a contact term and pion explicitly. And then what we do beyond the leading order, I put here. So we have a static and dynamical contributions to the interaction. And what people in chiral AFT plus many body are doing, I'm not sure how to compare because this is perturbation theory. And my major question,
Well, not quite right. It's perturbation theory in the potential, and then you iterate these in a Schrödinger equation. So you're generating a bunch of stuff that you also.
yeah, I think we should talk
In-
more about this because I really want to understand, in particular, these intermediate propagators in the high orders, because they are calculated in the vacuum.
These are irreducible diagrams. So you get a potential from these diagrams.
Yes, I understand.
Okay.
And then you take it and you put it in some many body model.
Typically, that's the way it's
Yeah,
done.
and
Then-
this is wrong. So you
well,
shouldn't do that. I mean,
agree to some extent.
okay,
totally different.
we have to somehow map this to exact theory because we know exact theory and we should be able to somehow see what is there, what's not there. As I said, this is calculated in the vacuum, but if you are in the big nuclear system, this process is there, but it's happening in the medium and you have
Oh,
coordinated.
but there are people working on that in the medium, and they take that into account. They just use.
Is this
these-
in medium randomization group?
know that, for example, like Jeremy holds, they derive like, in medium versions of these.
Yeah, that would probably a
So
better.
this is done. I'm not sure if you need that for medium mass nuclei, but there are people doing this in medium basically.
Yeah, that would be the correct way of doing that. But then you cannot use it in a standard many body method because then you have this double count. If you put this here, you will have.
I'm not an expert in how they do it, but the way this particular thing is done, you're iterating this at some order. You say this is my potential, it's somehow
Mhm.
derived from the microscope.
Okay, I will look it up. So I think that would be the right way of doing it, but not everybody is doing it. So they have superfluidity in nuclei. It means that we have a phase transition, and that's there for almost all nuclei. For open shell, there are very small. There is a very small amount of closed shell systems. If you have to deal with this particle and particle Hall channels coupled, and that's how we do it. So we do it in the dynamical kernel by keeping all this particle number violating terms. So particle number here is not a bug, but it's a feature. So we use the fact that the solutions for HLP and QRP like equations are the same in n+2 and n-2 nuclei, and we can take this into account. And then in the Bogoliubov space, we can make a rotation. In the number space, we can make a rotation, and then all these complicated contributions, they basically collapse in one term. And all the complexity is transferred to the vertex functions. So this has to be added then to HFB, and we can proceed in principle very similarly as for the closed shell nuclei. So what dynamical kernel does, it does a fragmentation of states. For example, this is the picture that you see. In the mean field calculations, you see Hartree-Fock or Hartree-Fock-Golubov states. And then if you include the leading contribution, at least that we call quasi-particle vibration coupling, based on our emergent formulas of vibrations, we see the fragmentation of the states. So in the beyond mean field approach, we see this kind of picture. Usually close to the Fermi energy, there is one dominant level that's usually observed in experiments. And further down or up, there is a strong fragmentation that's also observed. There are data on this. So what does it do for the response? You see for the transitions, if the states between which we have transition are fragmented, that naturally we have more possibilities to have those transitions, and that's what we see in the excitation spectrum. Instead of single states, of the few states of excitations, we see fragmented spectrum. So this is an illustration from a realistic calculation of very heavy nuclear system. Z equals 120, very neutron number. And this is how approximately the single particle levels look like. We still see something like a shell gap. This was done to probe the next shell gap after 126. In both protons and neutrons, we have the shell gap. That this shell gap is getting smaller because of the interplay. Basically, we have an interplay of the particle vibration coupling coming from the dynamical kernel and superfluidity. And we had some analysis of this guiding possible future searches of the island of enhanced stability. This is another example. These are dominant states and spectroscopic factors in T120. So this is just relativistic mean field calculation, black bars. This is done with the nonlinear meson exchange forces, and this is after adding the quasi-particle vibration coupling, and we see that it's better agreeing with experimental data, especially in the proton domain. So in the neutron domain, part of the effect was absorbed in the pairing correlations rating. It's not so big, and a strong reduction of the spectroscopic factors that's also seen in experiment can be reproduced.
What are those extra states you see in the neutrons that have no correspondence to the experiment? But they're just way off, and
There are no data.
so they might be there, but they're not measured.
Yeah, they're not. No, they are there, but they're not measured. This is an open shell nucleus. As I said, the states are strongly fragmented. So they see sometimes different several fragments with reduced spectroscopic factors, 0.3 or 0.2, something like that. I picked just one to compare for that example. They're very difficult to measure. That's what I wanted to say. And there are data on heavy nuclei that show a very strong fragmentation of deep hole states that we can reproduce too. So yeah, we did many studies of this phenomenon. For example, we could reproduce the spin orbit splitting in cipher 36. This was the neighbor of the so-called bubble nucleus, silicon 34. It was extensively studied experimentally to discover the density depletion in the center, and it was attributed to the spin-orbit interaction. So we could show that we can better describe this effect.
Question, can you give the systematic uncertainty from your model, from your theory side?
Yes, yes, I will mention this.
Okay.
So, we had some quite successful applications of the method to spherical nuclei for different phenomena. The problem was to extend this to deformed nuclei, and as far as I know, the deformations are particularly interesting topic for this workshop. So it was very difficult to do macroscopically beyond mean field calculations. So there is a number of mean field calculations that can be done in the deformed bases, axial and also triaxial. However, beyond mean field was extremely difficult, mainly because the interaction matrix elements and in addition, the form and coupling vertices have to be extracted from the many runs of the mean field and QRP calculations. It was very computationally prohibitive. However, recently we had a new method that's called finite amplitude method that can be applied for relatively fast calculations of deformed nuclei. So basically, we have a very fast. We can have a very fast run for the I'm trying to avoid some jargon. We can have a very fast run of quasi-particle interface approximation calculations that we can extract the formats. So basically, the problem was not even theoretically the problem was not even deformation, but it was mostly pairing correlations. So there was no formalism to go beyond mean field, keeping full HFB pairing, and this is basically the same for spherical and deformed. So deformation was not the issue theoretically, and we had to develop a method how we can extract this vertex functions that I was previously showing from the variation of the quasi-particle Hamiltonian. So that was not known before. So technically what we do, we run the QRPE calculation. So QRPE, in short, it's a calculation for the response function with only the static kernel. So no dynamical kernel, that's more complicated. But this static kernel is adjusted on the mean field level. So we can have a reasonable formats and we extract them from the peaks of those excitation functions here. So this is an example for silicon 38 with relatively large deformation. So we run for different J's and K's and then apply this procedure there. So then
so this 0.31 is something that you compute.
This is a self-consistent deformation of the mean field. So we run relativistic H of B calculation for generating the bases. So we generate the bases with effective interaction. So on the second step, we run the QRP calculations for these excitations. And that basically constitute our phonon input, vertices, and images. And then after that, we extract these vertex functions for different J and K, and then we put all this in the Dyson equation. So, and then as I mentioned, we get the fragmented states. So this is the picture that we get for silicon 38. So each of these state, this is it's in the canonical basis. So we have fragmentation because of the quasi-particle vibration coupling and also because of the pairing. So we have reduction of the occupancy, occupation probabilities, let's call them occupancies, and fragmentation. So we could also plot something like a Nielsen diagram. This is the famous type of representation when you want to show how the single particle states evolve with deformation. So we could do it also beyond mean field. So this is just pure mean field. This is beyond mean field just for the dominant state. So we pick one state with largest spectroscopy factor and put that in the Nielsen diagram. So this is remarkable in a sense that you can see you generate new shell closures moving along the deformation axis. However, of course, in the reality, there is only one deformation which is real. That's 0.3. This should be here. But also here we have a kind of a shell gap that was not present in this picture. So you see that the effect of the beyond mean field correlations is significant.
So on the previous slide,
Mhm.
just so I understand it before, one more back. This beta 2 is the beta 2 of the mean field that minimizes the energy.
Yes.
Okay.
Of course, we can try to, well, I was thinking how we can play with that, because if you add the correlations to your mean field, of course, you also change the geometry. And that would be really interesting to quantify. So I think we are on the way on that. But what I expect to have, I expect something not like an elliptic nucleus, but some irregular shape, because it will include all this quantum fluctuations. We can call them, of course, in some language you can call them quantum fluctuations of the surface that come from these vibrations to couple together. That would be really interesting to consider. And then we can still speak about deformation parameter, but I think it will be more complex, not just described by one parameter. We can try to, I think we should try to plot the density distributions and see. How much time do I have? I'm slow.
Well, yeah, we started pretty late, so.
Okay, but there is still a lot.
No, but you can take 20 minutes more. You can take more time. 10 minutes more.
Okay. So let me continue.
Can I ask a question? This deformation, in the PGCM approach, they actually expanded the deformation space, right? They basically do a linear superposition of different deformation and try to minimize the energy. In your approach, how do you? I mean, suppose you have the HFB states you start with some kind of deformation, and your minimization procedure will actually also lead to a different deformation after include all this dynamical effect.
Yeah, I think these approaches are complementary. You can either do a PGCM, combine different mean field states together, and generate some way correlated state, or you can do this type of approach, pure mean field. So
Okay.
actually, what I think it was a discussion also shown here. What happens in this? I think this is more microscopic what we do, and it's more related to the exact equation of motion. So there is more physics in there. So you see that there are very low lines. They can be very low line states in the spectrum. Imagine we pick each state with the relevant deformation. So we stick to the realistic deformation here. So at certain value, we pick those phonons from the spectrum. And the most important phonons are very low line ones. So imagine you have a very low line vibration, say quadrupole. So it does this, it does this, And then if you send the frequency to 0, it does this. So it freezes.
Okay, but my
That's
question,
why having low line vibration is physically almost equivalent to having a deformation.
right? My question is like in PTCM, right? So you're also limited by the collective coordinate you choose to use. Like for example, if you only vary it in the beta 2 and the gamma, you do not capture the octuple deformation. My question is, in your approach, would you actually pick up those high order, like not even high order, but
Yes, they come from with the octuple phonons. So this line here shows the octuple phonons J equals 3.
Okay.
And we have not just octuple deformation, we have, okay, not so many, but quite many contributions from this octuple channels.
okay? So this means you're not limited by the collective space you impose in the very beginning. You can dynamically probe all
We
the.
do not have collective space. You have only microscopic variables here. I
Right,
mean,
but
you can call this collective coordinates probably, but they are calculated microscopically.
yeah, I understand. I'm just saying the PTCM, if they want to explore the beta 3, they need to include the beta 3 in their coordinate, right? But in your case, you
This
don't.
will be this octuple phonons.
Right, okay.
But we have not only octuple, we have quadruple octuple, and then we have J equals 4 and J equals 5 there. So all K numbers. So 18 types of phonons here, and each have a certain spectrum. So.
Thank you.
I agree that would be interesting to compare PGCM. That's something we didn't do. Thank you for your question. So just one more example, and this topic we also can handle big nuclei. So this is Californium 250. So as you saw from the structure of the broadcaster, it's related to the neighboring odds nuclei if you start from the even. So the poles of the broadcaster correspond to the states. So that's why I'm showing it in this way. And again, we have the compression of the spectrum in both cases. The description is not so good here. Here is a bit better in the neutron sector, but we are still working on this. This is the very first implementation. So basically, this solved as a long-standing problem of the DFT, which consistently gives too low density of the single particle states. Now let me move to the response. So this is more related maybe to the topic of the workshop. The response function, as I said, it describes excited states. In this formulation of even system, so for even odd, we have to solve three-body equation to be accurate. So let me focus on even. So that's roughly our beta cell Peter Dyson equation that I showed before. And as I said, if we have a phenomenological effective interaction here, we add our dynamical part and we subtract the static limit of the dynamical part to avoid the double counting. So mapping to the phonon description gives us this. It's not going the way I want. Sorry, I wanted to show actually to show
just use
this
the
baseline here.
If it's easier, just use a trackpad with your finger.
Right. So that's what I wanted to show. This is so-called conventional nuclear field theory kernel that was obtained still by Bohr Morrison in the 50s and 60s by just inputting this collective degrees of freedom. In the extended theory, we can generalize this. So it's not just theoretical exercise. We get the idea how we can extend that, and we can extend that in iterative manner. So we can, for example, solve this equation for the response function with the phonomons inputted from phenomenological calculation, calculate this, and then plug this response function back into the kernel and reiterate. So in this way, if you reiterate twice, we basically get included those contributions, 3 loop diagrams, without evaluating them. So just by recycling our response function. So I probably skipped this. This was done for a colloquium showing how the interplay of single particle immediate trajectories and the connective states. Here is just briefly a classification of which we use for the nuclear excitation modes of collective character. So they are classified by the transferred angular momentum, isospin and spin. So this is the breathing mode, the monopole resonance. This is the dipole resonance. This would be just translational mode, quadrupole, isoscalar, and then there are an isovector, and then there are spin flip modes here. The most famous is gamma of Teller and the spin dipole mode that's responsible for the beta decay and first forbidden allowed and first forbidden transitions. So that's our classification. So what we do, we take our response function and contract with the operator of external field that corresponds to the mode that you want to. So here are some results from our past calculations. This is the giant dipole resonance. This is the most important, most famous excitation mode in nuclei because it dominates the spectrum. So you see a broad resonance. And this picture demonstrates the ability of our method to describe not only the position of the giant dipole resonance, but also the width. So if you do just mean field plus QRP calculation, you get this black dashed curves. This for nuclei, and gives you very good description of the position. So the energy is typically reproduced well, except for some cases. We have an ongoing discussion about the monopole resonance, that's a bit more complicated. But usually it gives a good position, but it cannot describe the width and also cannot describe the details of the spectra that are most needed for astrophysics. What happens in stars, the nucleosynthesis, neutron capture, beta decay, this all happens here. And this kind of description often doesn't even return any states in the given area. So here is just a general, so to say, low resolution calculation that shows that we can describe the width of the giant dipole resonance. So that's the red curve. I call it RQ-RPA, so relativistic QRPA for the black, and RQ-TBA, that's the name of our method, relativistic quasi-particle time-blocking approximation, because it was derived first as a time-blocking approximation, for the 4-point function, but now we can show that we can actually obtain the same result starting immediately from a 2-point function without any time blocking. But the name is still there. I just wanted to clarify. So you see this RQTB, this is the dynamical kernel. Yeah.
So for when you calculate these very different nuclei, is the underlying interaction, the two-body interaction you put in, the same for all of them, or are you adjusting
The
it?
same.
It's the same.
It's the same. So this calculation is done with the NL3 effective meson exchange interaction. It has 8 parameters. So the adjustment of this kind of interactions is done over the entire nuclear chart, but it has only few characteristic nuclei. So you have oxygen, calcium, some characteristic nuclei, typically 8 to 10 nuclei from oxygen to lead. And you adjust the masses of the mesons with minimal coupling and the coupling constant. So 8 parameters. And we have a little bit of freedom with the pairing interaction because it's not very well known. So we either use phenomenological value for it, or we calculate it from some finite range.
But it's the same for all of the things.
It's the same, yes. It's the same. So that's the idea to have a predictor calculation. Yes.
So the fact that in the calculations there seem to be a lot of structure and
Yeah,
features that-
it's smeared here.
and so that the reason that doesn't show up in the data is because of like resolution effects?
Because of the resolution, exactly. So what we do actually, we have our response function. We put some imaginary part in the energy variable, and you can vary this imaginary part. So what this imaginary part does, if you take the imaginary part of the pole with imaginary energy, you get a Lorentz distribution, right? So you get, instead of this, you get a picture like this, but you can smear it more. So, and this depends on the experimental resolution or how we want to show it. It can be very, very small, it can be larger, but essentially it's the same for the black line and for the red line. It's exactly the same to show that that this theory probably makes more sense. Because you can see also people doing just a QRP calculation and putting a large smearing parameter. And you can in principle produce the same data. But if you put one MEV smearing parameter, you will be perfectly on top of the data.
Is the smearing not determined by the particular experiment? What's the resolution of that experiment?
Yeah, that's a good question. Usually here we have discrete states. There is no smearing below the neutron threshold, somewhere here. Okay, so then you don't need any smearing. We see discrete states, and that's what we do in our work with people who are doing nuclear resonance fluorescence and Darmstadt, for example. So group, you see discrete states. There's nothing here. Here you start to have a continuum effect. So in principle, if you have very, very good, exact, accurate theory, it should give you an envelope.
Okay, so the smearing is partly from the experiment, partly because you're not having the continuum couplings that would otherwise broaden this on the theory set.
Exactly. We have a theory with continuum too. But usually, okay, let's say in the thin region, the continuum width of those states would be around 1/200 keVs. So it will not contribute much. But if you go to very, very, very small nuclei, it will be much broader. Already in oxygen, it's very broad. So the problem is to have many particle continuum. So we can have one particle continuum, that's fine. But somewhere here, you start to have 2 neutrons coming out. You have proton threshold here, you have 2 neutron threshold here, and then you have a deuteron alpha particle. That's why if you look at the data, you will see on the high energy tail, you will see very much bars. Difficult to say. There is no good theory. We are trying to think about 2 particle continuum possibly. But we need some more manpower, so nobody wants to do that. Yeah, there are some more resonances shown here, but the idea is the same. You have some peak or few peaks in the simple approach, and then you have the broadening, which is related to dissipations. Sometimes it's called damping, or sometimes it's called spreading, resonance, and so on. And this is all happening just due to the dynamical kernel. That's what I wanted to emphasize. And the better you have this dynamical kernel in the theory, the better this the description. So here is the case that we considered with Caroline Robin. That's her calculation. For the gamma-Steiner resonance, why is this important? This is the key to all weak processes, including those in stars, beta decay, electron capture, and other. So you see again our calculations with and without dynamical effects. So in this case, it's very, very different. So, and here is a high resolution, so to say, picture for the low energy parts for the three nuclei, 74, 76, 78. Why this? Because the beta decay half-life is determined by this energy range. So basically you have to sum of the strength in this energy range, which is called Q beta window, and you can get the half-life. So and with only the mean field theory, with the static kernel only, we get half-lives which are not very realistic, sometimes 2 orders of magnitude larger than the data. And here you should look at the red curve. So this is intermediate result. That's probably not important here. So the red is the leading contribution of particle vibration coupling gives us the very good description. There is no artificial quenching here, because sometimes people quench the GA constant, or sometimes they add something which is called proton-neutron pairing. That's something not really a good way of doing it. So now about
We wrap up in like 5 minutes or what?
So you were asking about uncertainty quantification, how we can do that. So this is now the calculation in 3 approaches. I picked just that giant dipole resonance to show this example. So this is a just pure PE calculation, only the quasi-particle configurations are present. So blue line is the leading approximation for the quasi-particle vibration coupling, one Farman. And this is this iterated approach that I mentioned, the red curve, where you have recycled our response function once. So I don't have like particular numbers attributed, but I think this can illustrate how you get your approach. It's basically convergent. We see that the changes are getting smaller, but they're still significant. So we have to go at least until this point.
Since you mentioned that these interactions, they are fit in some way, but also just vary your underlying body interaction.
We don't vary. So
But
this
you
is all
could,
done.
since you're talking about UQ, that's something you would, I would argue, you probably should be doing if you want to assess the overall uncertainty, because that's like one particular choice and it would affect the results presumably.
Yes, I've seen people doing that. Like you take some answers for your density functional, then you vary parameters to capture this or that properties.
Well, supposedly, since these are fit to something, there's anyway like some underlying distribution, and when you're doing these fits, they should come with uncertainties. You could propagate those things. That's what I'm talking about. Because you fit to like some observables, and you take a single value from that. But
You
fit
can do
would
that.
probably not be perfect.
Yes,
so
yes,
you
we
have
can,
like some.
we can do that. We can do that, but I'm not sure this is informative. I mean, you vary your parameter, you vary it randomly, because you cannot just change one parameter.
Yeah, you have to vary all of them
all
at the same time.
They are,
That's right. Yeah.
yeah, but how do you vary them? at the
Well,
same
by
time.
looking at the fit and see how well does the fit actually constrain those parameters, because presumably the fitting would give you some posterior or whatever.
Right, but with this given parameters, you have already the best fit.
There might not be.
So
any
any
reason-
variations will give you worse fit.
Yeah, but that's part of the uncertainty, because that best fit depended on a particular choice to fit those nuclei. And there's in principle an uncertainty from making a different choice, and in to some extent that's covered by the uncertainties you get out of that fit, which you could propagate forward.
Yes, I think we can do that. We can do that. But at this point, the problem is that our functionals are not ideal. So there is still ongoing research on the functionals. For example, even for this functional, Afanasyev, I think he was here before, some weeks before. He's doing this kind of investigations. And he just discovered this one parameter or two parameters just redundant.
Yeah, right, but then I guess the point was what you're asking for, since you can quantify the extent to which they're not ideal, and probably they will never be ideal. But if you can quantify that, and then if that uncertainty is less than all these experimental resolutions, you can just declare it.
Yeah, I think this can be done. So for the moment, I only have this for the many body part. So not for the,
So the
not for the
model,
interaction.
from the technique, not so much from the.
Yeah, yeah. So this is something to do in the future, but I think it would probably be more interesting if you start from the by interaction from the beginning. That's our.
That's assuming there is one unique pair interaction. For the discussion.
The parameters can be varied in the same fashion, of course. Yes. 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 Okay, I'll probably skip this. We have some quantum computation perspective of this models, but maybe I just move to the topic which is probably relevant to the intersection with heavy ions. This is finite temperature. So finite temperature here is not the trick to avoid some computational difficulties. This is in nuclear structure related to the description, or I have a missing bracket here, I'm sorry. So this is from my non-relativistic presentation. So, okay, I forgot to replace it. But actually the idea is the same. What we do, we replace the ground state averages by thermal averages. Yeah? And then we can formulate the equation of motion in the same so the same form for the response function. And the interaction kernel in the leading approximation also looks similar, but it has some new poles in it. Some new poles and new residues are now functions of the Fermi and Bose distributions. So what's the major player here is what we call thermal unblocking. So what happens that in the simplest leading uncorrelated propagator, we had at 0 temperature only 1 and 0 here. You can only have transitions across the Fermi surface. And now you can have transitions also on the same side. And that adds a lot of new states to the spectrum. And here it's shown how. So this is the giant dipole resonance in RPE and the time blocking approximation. So we can see that the fragmentation of the resonance still occurs. And here's a lighter nucleus, here's a more heavy nucleus. Both are doubly major here. However, pairing disappears anyway.
Should call what's the motivation to study the high temperature region? What's the motivation to study the not non-zero temperature?
So what happens in the stars? There is a certain temperature of the environment, and the nuclear states are distributed. So in principle, we need transitions between the excited states of the nucleus. So you have few low-lying states populated, and then when our process happens, you have transitions between the excited states. But this entire formalism that I was describing, it's only for the transitions between ground and excited state. So and this is kind of a cheap way how you can include the transitions between excited states on average. So you have all the initial excited states averaged because of this, and then you can use the Matsubara technique, and you can have a very, very similar approach to this. It's more complicated because you have this thermal block and you have more states, but essentially it's relatively easy. So and then we investigated the temperature evolution of those resonances. In particular, we saw that at very high temperature there is a low energy enhancement that grows. So it happens in all the channels, all multipolarities and nuclei. And we are now having a proposal with Lignaro to possibly measure this. It's very difficult to reach. But here in this picture, we can see that going to higher temperature, we see something. We observe something like low energy enhancement here. So we want to see this region below 5 degrees. In addition, there is a little redefinition of the strength function at a finite temperature. We have, on top of that enhancement, we have also the this exponential factor that comes from the detailed balance. So then if we put them together, we see even more enhancement. And that's something we see also in the data, in particular the data from the author group. And this is also active area of research, what's happening here, because again, our processes are all sitting on this low energy enhancement. So okay, I think I just keep the rest because I'm over time, right? So we have some more finite temperature calculations for the beta decay that served as an input for our process, and then on the GT plus side we have also electron capture rates, and finally a little bit on the pairing channel. So to investigate what happens with the pairing, with superfluidity, we need to consider this type of correlation function. And we did that too. And that basically leads to the same BCS-like gap equation. But now we have a new contribution from the dynamical kernel in here, so which can, in principle, change the behavior of the pairing up with temperature, in particular, the critical temperature. So at 0 temperature, we get an enhancement of the pairing at the surface. So that's the peak that's shown here. And then with the temperature growth, we see this famous behavior. And the pairing gap just drops. However, if you do just BCS with the mean-field interaction, it drops earlier than if you do it with the dynamical effect. So pairing, correlation, superfluidity may survive a little longer than this one. Okay, I think I'll simply stop here. Thank you very much for listening. I thank my collaborators again for funding, and I hope to have some more discussions during the workshop.
Very much. Any last questions? Remember that in the afternoon we'll have lots of time to get more in depth, but any quicker questions before then?
Sure. Can you extend to the lighter nuclei in your approach, such as oxygen 16 or neutron 2?
Yeah, I think we can still do oxygen neon. Yes.
Okay.
was gonna ask, so can this approach say anything about the neutron radius of a nucleus, or like the neutron skin thickness?
I think so. The problem is, yeah, you're probably aware, you're aware of the ongoing discussion about Syrax, Pirax
Yeah.
experiments, reconciling them within the different approaches. So I'm thinking about this. There is a way to access the idea of the neutron matter. But if you talk about neutron skin, you're talking about the difference between neutron and proton. So proton radii in the DFT-based theories, they're part of the field. So they automatically well described. So in principle, you put some, especially I was looking at the charge radii of lead and calcium. So it's about lead 208 and calcium 48 now. So they look good. So then you can look, what you would do first, you would look at the neutron matter radii in the DFT, right? Because this is like first step in this kind of description. So in the DFTs, in the different DFTs, you get different values. I was kind of happy or probably fortunate with this NN3 forces, because they were criticized so much in the past, as they were given larger neutron radii in the leptoid than the other functionals. But then, then we had the results of the Pirax, and we just realized that this functional is one of probably only one which describes this on the mean field level. So we have this 0.28 Fermi neutron skin in the NN3 forces. So it's doing well. But then if you look at calcium 48 within the same, we have the neutron skin which is larger than you observe in Syrax, a little bit larger. So what can we do with that? We can look at this radii in the Biermann field approach. So that would be the next step. Now the question is how to calculate them, because you can calculate them from the single particle spectrum, for example, based on single particle wave functions. But then we don't have a good double content removal procedure in that way. So we have a very accurate theory in the response sector, and here we can access the radii through the samples. And that's what I'm doing now. So basically, I could show that we get reduction of the sample in the calcium. I just published a paper on the monopole resonance. That's already in the second stage of the review. I could show that the beyond mean field response calculation can solve the monopole resonance puzzle. We have the softness, the remarkable softness of the tin and zirconium few nuclei that cannot be described on the midfield level, but we could show that it can be described in the field, the centroids of the monopole resonance. And the sum rule of the monopole resonance is proportional to the radius squared. So we see that the sum rule is moving, so we can possibly access this radii, but I don't have the numbers right now, because you have to invent some specific sum rules and see how they are saturated if you go up to high energy and so on. So we hope to have something soon based on these results for the monopole.
There's more questions, maybe let's postpone them to the afternoon in mind. So
Thank
thank you,
you
Lena, again. behind, but we should probably take a short break. Right? Or it's not working. So what do you think? Do you want like 10 minutes we should take, or how much break do we need? 15 minutes? Sure.